We're about to get started. Thanks for coming to my talk. I am Michael Spencer. I am a compiler engineer at Sony PlayStation working on Clang and LLVM as a C++ front end for our game teams. And so we're going to have this talk. My little optimizer, Undefined Behavior, is magic. An alternative title would be my little optimizer, any sufficiently advanced optimization is indistinguishable from magic. It's not really magic going on here, but sometimes it does feel like it. So getting into this, first we've got to go over some definitions in C++. Because the compiler doesn't just like implement the isn't just targeting the hardware, it's targeting the abstract machine, or trying to lower the abstract machine down to the hardware. So well-formed program, it's basically a program that compiles successfully and doesn't violate the one definition rule. Then there's implementation defined behavior. And so that's basically, there's lots of things that just says are implementation defined. And that doesn't always necessarily mean that it's going to do something nice. It can like launch NetHack if it feels like. That is generally a valid implementation defined behavior, but standard's not designed to protect against malicious implementations. So we're generally okay with that. And we've got unspecified behavior. This is like, it's not always enumerated when it is. Like there's a note here, generally it is, but not always. And these are for things that, a reasonable implementation may not be able to guarantee any specific behavior. And so it's not required to be documented. And then we have our favorite, undefined behavior. So no requirements at all. Now, what are implementations allowed to do with undefined behavior? No requirements for the entire execution of the program. So if you have undefined behavior anywhere, your whole program is like can do whatever it wants. So what do implementations actually do? A lot. Now, the most common thing that's going to happen, you're going to see in examples here, is that the compiler is going to say, undefined behavior can't happen. And since it can't happen, then I'm going to optimize assuming that it can't. So here's a really simple example. This is quite similar to the Linux kernel bug, which was recently in the past few years. We've got this variable, okay, it's a bool. We're gonna check and see if we actually have a value and then call blah. But first we dereferenced it. You had a refactoring, whatever. It got moved up there. The compiler is going to look at this and say, if OK were null, we would have undefined behavior. OK can't be null. This must be false. Remove it. Just call blah. And at runtime, whatever can happen. You might get a seg fault, but it might just go into blah. And OK is not. It might be like some positive, or it might have a 1 in the low bit, and then thinks everything's OK. So how does the compiler actually reason about undefined behavior? That's what I'm really here to talk about. So we have a couple ways to represent it. And to backtrack for a second, I'm going to be mainly explaining how LLVM does things, because that's what I work on. But GCC and other compilers use very similar reasoning. So we have a way to express unreachable, meaning that this part of the code can never be reached. And we also have undef to represent things that we don't know what this value is. And then there's also implicit things, which is things that the optimizer knows can't happen. So we're going to take a brief detour into LLVM-IR. So for those of you that know LLVM, some of this, I have omitted some parts of the IR, just to clarify, or to simplify explanation. So we've got matching between, you've got your definition of your function, you've got definition over there. We have a load. That dereferences a load, so it turns into a load in the IR. We have our conditional, turns into an integer compare not equal against null. Our branch, the return, and the call. So generally, it should be pretty obvious what it maps to. If at any point, I don't clearly explain what the IR represents or it's confusing, you can interrupt and ask. Let's explain unreachable here. So it's an instruction, can't be reached. Right here we have this awesome program. We want to write out this value. And then we want to, like, let's say, I want to break up the debugger here. So I'm just going to dereference 0. That'll give me an segfault, right? Well, yeah. So this is what the optimizer sees. We've got a store and then a load from null. Now, it comes through here, it looks at the store, that's OK. It looks at the load, sees load from null. Well, that can't happen. It's undefined behavior. That can't be reached. Replace it with unreachable. We also have GCC and LLVM or Clang support this built-in unreachable that you can use, generally used for some optimization stuff, but that's how we're going to represent it here. And so that means is that everything after it can't be reached, and everything before it can't be reached either. So we just deleted that store. We don't know what that was storing to, but we clearly can't get here, so we'll remove it. Then we have undef. So here we have A uninitialized. Let's use that to like get some extra random seed for our random number generator. Well, optimizer's not going to like that. So here's how it's represented. I did fold some stuff away. So essentially, it's going to be A equals undef because it's uninitialized. We don't have a definition for it. We're going to load from P, and then we're going to return. Then we're going to add P to A and return it. So the first thing the optimizer does is it looks at that add, and it just turns it to undef, because undef is basically represented as it can be any sequence of bits we want at any point in the program. So here, any fixed value plus an unspecified value is going to be an unspecified value. So we can just fold that away. Then star P is no longer used. A is no longer used in the return to calculate the return value. So we just delete all that ed code and turn undef. Some subtleties about undef is it's not always going to fold to undef. So here we have A equals or X in undef and an and. So you could get this value if for or you chose all 1 bits, and for and you chose all 0 bits for undef. That's a perfectly reasonable thing to fold it to. You can also fold it to this if you chose all 0 bits for or and all 1 bits for and. What about this? I can't do that because now you've gotten rid of the information about X. It's not possible for that to happen. Now this one's an interesting one. Is you want to like clear a register, you XOR the register with itself. Doesn't matter what's there, you'll get 0. Well, an LVM, our representation of it, when you XOR could be any value at every time it's looked at. So that folds to undef, not to 0. And then you divide by undef, there's undef. So implicit undefined behavior. Signed math can't overflow or underflow. So A minus B is greater than -1. So this looks like this in IR. Now we've got a new little thing here. NSW, no signed wrap. If underflow were to happen, this would have a poison value. And so the compiler looks at this and says that since A minus B cannot underflow, A minus B will be greater than -1 if A is greater than or equal to B. So we removed the subtract and just folded it into the comp. So the kind of undefined behavior is type aliasing. So here we've got an int and a long. We're going to store to 5, store 5 to h, store 6 to k, and print out the value of h. But we were sneaky in main and cast our value to 2 different things. So, and this is what's, this optimization is going to be known as like F strict aliasing or F no strict aliasing is what's going to hit this. So this is what it looks like in IR. This is a simplified representation of how we do type-based alias analysis. But we're going to say for this that that string after the TBAA is loads and stores only alias if that string is the same. So the store to h and the load and the store to k, by asserting that like int and long are the same thing, then they can't possibly be storing to the same value because we just said that. So we can actually store to load forwarding and just put 5 right there directly. Don't need to load. I got another example here. loop termination. So this is actually a fun one from John Reiger's blog. He actually has an awesome blog, Embedded Academia, and he's super serious about undefined behavior. So if you want to know more, read his blog. But here's an example. So we're going to calculate Fermat's last theorem. Well, we're going to evaluate it. And if we ever hit a case where it's true, then we're going to return 1. Otherwise, we're just going to keep looping over. Now, what does this print? Print's disproved. How'd the optimizer do that? So it's actually pretty simple. But this is what the IR looks like, ignoring. So this is just the control flow. Wasn't enough room on the slide for the whole thing. But the only important thing to note here is, so this is raw from Clang without optimizations, is that this is the only return. It didn't even code gen return 0 because it's trivially dead, because it was a while one loop. Can't ever break out of that. Well, and there was no break. So since we know that, and we have this little pass, interprocedural, sparse, conditional constant propagation. Anyway, basically just looked into Fermat, saw the only thing it can return is 1, so we can just clearly forward that through and do control flow graph simplification and just print out disproved. Now, this still hasn't actually changed the behavior of the program. We're still going to run Fermat. If it ever returns, we're going to print true. Or we're going to print disproved. That's already what we're doing. What happens next is that the optimizer also looks at Fermat, and it says, you know what? You did not read or write machine state visible to the caller. So we're going to stick read none on there. Then we take a step over to the standard. And implementations may assume that a thread will eventually do one of these things: terminate, I/O, volatile access, or atomic ops. This does none of those, and it doesn't do any of the bottom 3, and it must terminate, so we can just delete it. We just proved it. Now in C, explicitly, while 1 is one of these protected classes, so we actually have to add an additional attribute and saying, oh, wait, you can't remove this in this case. But not for C++.
Do you think C++ should get with C's program on that?
Is infinite looping a useful thing when when the compiler can prove that you have no externally visible state? If it is, well, then we need to provide a way to express that. Not necessarily always doing it. Because yes, do that. There's lots of things you can do. The while 1, though, may be reasonable. Not sure. But other people can decide that. So we got an example on object lifetime. Some more awesome code. You'll notice all the code in these examples or on these slides is just beautiful and awesome. Great things you want to write. So we've got this pointer. Let's open up a new block, make an int, store the address, and then dereference it. That's a perfectly reasonable thing to do. This is what LVM sees. We've got our, so the alaka is basically just alaka in C. It just allocates it on the stack. And we get these lifetime markers. So lifetime start, loads and stores to A before this are dead, because it wasn't alive before then, so clearly, why'd you touch it? And lifetime end, loads and stores of this after this are dead. So we look at these loads and stores, and that loaded from A, well, that was dead. Let's remove it. And now that store, well, nothing's loading from it, and we're about to end its lifetime, so we can remove the store. And clean up everything else. Yeah, you didn't actually want to do anything in that function. So references. Does this look good? Yeah, references you can't bind to a null. And so here's the IRCs. We've got a new little thing here. Dereferenceable. This means that you can, if you read from A, it's valid to read up to 4 bytes. So the optimizer looks at this integer compare against null, says, A can never be null. That would violate this. Let's fold that to false. Then let's do some inlining, fold that to false. Now, this example was actually, JF told me about this example. This is from a recent bug from V8. They decided that instead of taking up an extra field to represent these different types of things, they were just going to use special pointer values. And they chose that 0 was a great pointer value for none. Then, if you want to, so I want to check if this thing is none. Well, let's just, this equals none. Now, this always has to point to a valid object. Can't be null. So it looks like an IR. We add the non-null tag. Now, we actually had to back this out because it broke a ton of code. But yeah. But hopefully it can eventually go back in. Once we get everyone to use Undefined Behavior Sanitizer, it'll flag it and we'll get rid of that. But yeah, so inliner, or sorry, optimizer. Well, yeah, so we'll inline first, inline the none. It's just null. Now we have an icon against null. Oh, look, can't be null. Hold that. Can't be null. Oh, look, it's false. And hold it again, false. Oh, look, we can never be none. Yeah. Took quite a while for the Node.js guys to get through that bug. This was actually like just in the past month. So now, signed under overflow. This is actually like a really hotly debated thing, is how much does this actually help? I'm not going to be able to answer that question today, but here are some of the optimizations it actually does. So we're going to multiply by 20 and then divide by 2. Well, since if that could overflow, then we can't just change that to 10, or just change that to a multiply by 10. But since we know it can't, multiply by 10. Got rid of that expensive diff. Multiply by a constant and then compare against 0 specifically. Well, we don't even need to multiply because the scale doesn't matter. All we're comparing against is 0. Now this may look weird. We don't have a negate in LVM because it's really simple to just do subtract from 0 to negate. So you're negating two things and then comparing them, sign greater than. And then where 4 is x and 4 is negative x and 5 is negative y. You can just do that and just swap them. No need to actually fully do that. And none of these optimizations can be done on unsigned, or if you have if we made signed overflow be defined behavior. Now, what this actually can hit is promotion. So here's our element access function. We're just going to add x and y and access into A. So here's what the code looks like for signed types. And so we've got the no signed wrap and the sign extend. The get element pointer is basically just the index operation into A. Then we load. So let's make that uint and look at the code here. It's basically the same. Only difference is that we now no longer have the no signed wrap, and now it's a 0 extend. So when you lower this to x86 assembly, there's a difference. The difference here is that we do that add, but it could have overflowed. And so in the unsigned case, we have to make sure that we only take the low part. In the signed case, we can just use the 64-bit value directly. And you have to use 64-bit values for this addressing mode. Which one's better? The shorter one. Shorter is always better. Not necessarily true, but. And so in this example, it's like, oh, it's just a single extra instruction. Well, like that can add up like with all of your accessing functions. You got to do that, and on each step you could have to. And then when you actually add it into a loop, so here's our pretty simple loop. We're going to template it. We're going to do it unsigned and unsigned. and raw IR. So this is actually what the messy IR looks like. This is actually not completely raw. I ran, did I? It has one pass or something. It has a little bit right over it. But if you actually want to see the raw IR out of playing, run all that. You have to do O3 and disable passes, because if you don't do O3, we actually omit some information, because later passes will all unconditionally use that for optimization. But after a little bit of cleanup, we've got a pretty simple loop. On the left side is the signed, and right side is unsigned. So explaining this loop, this is the first time we actually have to deal with this, where since we're in a loop, I can change each iteration. And LVMIR is a single static assignment form. And that means that you can only assign to something once. So a way to represent that is just basic block arguments, where when we come into body, when we come from the entry block, we just say that it's 0. And that's done right there. And then when we're coming from the loop back edge, we say that it's the new value of I, which we added 2 to it. So it's new value. And first we do a little bit of cleanup. We gotta clean up the loop so that this we can do some magic to it. Up here, move the add up. The add didn't actually change anything. It didn't change the value of I if we have to exit. And then we simplify the induction variable. And we just added a bunch of new code out there. Why do we add all this new code? Well, you'll note that we return ret. Ret's here, takes 4. 4 is up there. This whole loop body is dead now. We were able to completely fold away that loop. Why were we able to do that? Well, because if we go back to our original C++ code, all we're doing here is getting in and getting the even value less than or equal to it. So if n is odd, then it gets n minus 1. And if it's even, it just returns n. And so if we look over here, that's exactly what this is doing. We compare n against 0, because if n is negative, something weird happens. I think you get undefined behavior here. Or
It'd be a non-terminating loop, right?
yeah, which is, can't have a non-terminating loop, so undefined behavior. And then we just do a max operation. Then we add 1, and then actually remove that 1. That just folds to an and of the remove the low bit. While our unsigned case actually still has the full code, the full loop. Because when induction variable simplification came in, and it does, that's actually part of the optimizer I don't fully understand. But basically what it does is it looks over, so I is the induction variable. It looks at that, and it actually forms some crazy mathematical expression about how it's changing every time, and then looks at what the beginning and end conditions are, and uses that to try and either simplify it or completely remove the loop. And it failed on unsigned because with +2, if n is unsigned in max, this actually becomes an infinite loop. Now, infinite loops, we're not allowed to have those. Technically, they could have folded this thing to, I don't know if it's allowed to fold to undef. I think it might have been, but it could have gotten rid of it. It doesn't actually do that, but that's basically one of the, but the signed versus unsigned is, it does heavily limit the reasoning that these optimizations can do.
But in this case, because if you rely on the fact that infinite loops can also not be present, then in this case the code should have been the same, right?
No, it could have produced the same code. That's perfectly valid, because I believe that this can just be, it becomes undefined behavior,
Yes.
and then it can become whatever it wants.
But it didn't.
But it did.
But it didn't. LLVM doesn't was not able to reason that far.
Would you recommend using signed types over unsigned types in loops whenever possible?
For indexing and for your loop bounds, anything that has loop bounds or influences the loop bounds, yes. And use sanitizers so that you don't, and good fuzzing so that you can actually figure out if you do ever accidentally overflow. But in some loops, it doesn't matter. But there are loops where the difference between signed and unsigned is like 25% because it's able to get rid of a lot of weird sign extending stuff it has to do, or it's just able to much better calculate loop bounds. So our next example here is realloc. This was actually another one from John Reger's blog, which was actually, so he held a contest for what's the craziest undefined behavior you can find, or the most surprising. And Nick Nowicki, who used to work on LLVM, submitted this one. So what do we think this prints? Can anyone guess? 2-2.
I'm guessing 1-2.
Yes, 2-2 is a reasonable guess. You would think so. If P and Q are equal, they have the same address. How can they print different things? Yeah, 1-2. How does LLVM do this? So I thought that this was going to be actually a little bit complicated, but it turned out to be pretty simple. So here's the IR. I did omit the branch. So the only thing missing here is this if P equals Q, because it actually has nothing to do with the analysis that the optimizer does. You'll note another new keyword here, no alias. So malloc and all the allocation functions have this property that the return value aliases nothing else in the program. And it's included realloc. Realloc may choose not to move anything, but it still invalidates the old pointer. And we model this. So we put no alias. So we've got the store to P, store to Q, load P, load Q, use the values. Store to load forwarding comes in here. It goes to look at P, or at the load of P. It goes backwards, finds the store to P of 1. Then it looks to see if anything could have invalidated that. And it sees the store to Q. It goes and does some alias analysis and says, well, P and Q can't be the same value because we've got this no alias attribute. So you know what? We're just going to forward that. So call 1 and 2, or print 1 and 2. And that if doesn't even matter. At runtime, they happen to be equal, so prints 1, 2.
Why didn't it say the if was false because they're not aliases?
It could have done that. Does not. Sorry.
I think our alias analysis is supposed to be it's not a property of the pointer values, it's the property of the memory to point to.
All right, so the question was, why didn't it prove that they were false? And Richard over here, they pointer equality and memory equality is orthogonal. All right.
Is it completely orthogonal, or will non-alias pointers guarantee comparing not to each other?
I don't actually know. I don't remember what LLVM guarantees there, because there's when you're at this level, there's the LLVM Langgraph. What do we guarantee about our IR? And then there's actually C++. And it's Klang's job to map C++ semantics to LLVM semantics. But so I don't actually know. I don't even know if Richard, do you actually know if by language rules if you'd be able to assume that was false? Maybe. That's an interesting one. This one. I really like this example. How much do people think that we can optimize this? We've got sequentially consistent stores and loads. Sequentially consistent means that there's a total ordering across all threads. This is the only thread we're looking, or the only function we're looking then that the optimizer might not know about anything else in the program. You can just see this, and it knows that we've got X and Y. So any guesses about what we can optimize this to?
You have to do the store, but you can elide the letter because they might happen. They happen so close together in the that you can assume that they happen so fast that no one else can observe it.
You don't have to modify the x around the atomics.
Which?
So that x of 0 and the x of 1, I think the before can be moved after.
Do I still have to store 0?
Actually, no, you don't.
Or if the two are globals, the ones that get initialized automatically.
Well, they have been, and it may have been written to something else. It doesn't. That part doesn't matter here. So this is what we've got in IR. Our store, and then LLVM explicitly models atomics, because turns out there are optimizations you can do on them. So we've got our sequentially consistent store and a sequentially consistent load, comparison, and then some branches and store if it was 0. So the first thing we do is what you said, which is we can forward that. And why can we do that? Well, because while there is a total order, we can assume that, or not just assume, we can just say that, oh, our total order was this, and nothing can observe, could have observed the difference. So we fold that away. Now we've got this. Now, can we remove that x equals 0? Well, let's take a look at what the standard says. Bunch of words. But basically what this is saying is sequentially, we have a total order of all loads and stores in the program if data race free. And if you look here, can another if another thing reads x, so another thing is waiting on 0 on y to be set to 0, and then it reads x right after that. Is that a data race?
Can't read X without race.
Yep. So that's a data race, and guess what? We can't have data races. So remove that store to the store. So this was surprising to a lot of people. It was a bit surprising to me, but after reasoning about it for a while, it's like, yeah, you can do that. LLVM doesn't do this. GCZ doesn't do this.
Are there any compilers which take liberties on atomics that they would not take on volatiles?
Yes, and I will plug a talk about this later. But we do LLVM does do a few things. It's just not aggressive. We did at one point we were a little bit aggressive, but it was either wrong or we weren't sure about the model or something, and that got backed out. And so we're pretty conservative right now, but we can be more. And I'm not. GCC doesn't do this. I don't know if it does other things, but they're definitely allowed to. So we've got all this undefined behavior. What can you do about it? Because you're things go wrong. Your program doesn't work in an optimized build. It works fine in debug, and you have no idea why. And because the compilers are now so aggressive about undefined behavior, the result just makes no sense. There's paradoxes. This value was both true and false at the same time. Everything's going crazy. Well, first thing, warnings. W all, W extra, W error. These warnings will actually catch almost all of the examples here. But no one writes code like this. Generally, these undefined behaviors will come in through inlining or through more complicated things. So sanitize and fuzz. You've got address sanitizer, undefined behavior sanitizer, thread, memory, and now efficiency and data flow and a few others. But so for my testing, I always run undefined and address because you can run them together. And that caches so much, and it points you exactly to where it is. There have been lots of talks about it, about these sanitizers. So if you haven't used them yet, you definitely should. But if you're doing this, it's runtime, so you have to have good fuzzing and good coverage. And static analysis. We've got Clang, Coverity, PBS Studio, among others, that will all help you find these bugs. So what is the committee doing about this problem? Well, is it a problem? But what's happening in the committee about this? So SG12, Undefined Behavior. We've got a study group for it. What have they done? Well, in C++17, we have strengthened the order of argument evaluation. It is not totally ordered, but or does not have a guaranteed order, but you are no longer allowed to slice. Like, it's no longer, like, you can't, like, interleave all the operations at the same time. It's like, it happens in some order. We also got rid of undefined behavior we are getting rid of undefined behavior in the preprocessor. That one's not actually going to hit you at runtime, but it's like, there's no reason to have it in the preprocessor. Like, I don't know the examples. There's some weird, like, if you paste tokens in the wrong way and form something, it's like undefined behavior, or there's weird things. Like, compilers are good. They don't like erase your hard drive when they hit that case. But again, malicious compilers. Making memcopy safer. There's some things that you currently can't do with memcopy that programmers expect to be able to do. And so we're trying to make those things well-defined behavior. And in general, getting rid of unneeded undefined behavior. And that can be really controversial. Like, oh, do you need this? Do we need this? But there are some that are pretty uncontroversial, where it's things that, like, this is something that every programmer does, and like, compilers don't want, like, they don't even really want to optimize it because it's not useful to optimize, but it's currently undefined. And those kind of things are good to get defined, are pretty uncontentious. So if you're interested in more undefined behavior, there are some more talks here. Chandler will be giving a talk, which is much less about the, like, why is the compiler doing this, and more ways of thinking about undefined behavior. And Jeff, as his no-sing compiler, would optimize atomics. Not entirely about undefined behavior, but much more in detail about atomic optimization. So, any questions? So I actually had a friend who's an artist, and what's up with the pony? I have a friend who's an artist that I was like, she was like, I might be opening commissions up, and I was like, do I actually want anything drawn? I was like, you know what? I want an LVM pony. So made that. Then I showed it to some people in the LVM community, and JS saw it, and he's like, you know what? We should do an April 1st post. So we actually planned that, and JF wrote up a blog post about where it was like changing the motto to LVM, undefined behaviors, magic. We're gonna, like, there's been all this discussion about undefined behavior. Now we're gonna be all nice about it, or something like that. But that was pretty fun.
Why is signed integer overflow undefined behavior while unsigned integer overflow isn't? Is it just some historical accident?
So why is signed overflow undefined behavior but unsigned not? So the reason I originally heard for this was that back in the day, there was one of the processors would trap on signed overflow, and so it's just like, it's undefined behavior.
Is it still relevant today?
So the C++ standard does not guarantee two's complement.
Yes.
But are there any real-world architectures that
Ask IBM.
Yes, ask IBM. And yeah, so why, like, they could have chosen implementation defined behavior, or like delineated a set of behaviors, but so I don't know exactly why it was originally. Now though, it has remained so because compilers make heavy use of this information while optimizing.
Has there been any similar repurposing of certain other things that are undefined in the C++ standard? The example I'm thinking of being pointer comparisons in unrelated pointers is undefined, but std_less is defined, I recently learned. Is
Yes.
that used by the LLVM optimizer at all, or is that something they...
I did try an example with that. I wasn't able to get, oh, sorry. Again, repeating question. So comparison of pointers to different objects is undefined behavior. But std_less can compare any pointer and it's well-defined, or any two pointers and it's well-defined. I forgot actually the last part of that.
So the question is that something the LLVM optimizer
Oh,
or
yes.
any optimizer can use, or is that something the working group should cut from the standard as extraneous undefined behavior?
Is that something that the optimizers can use, or should it be cut? LLVM doesn't currently use it, or that I'm aware of. I think GCC does. There was a, that might have been pointer overflow. I'm actually not sure if GCC does. So I'm not sure I can actually answer that. If nobody's using it, it could be considered, but it also doesn't really make sense to compare pointers to different objects.
Well, std_less allows it.
Yeah, it does. So, and the reason why is because you can convert to int pointer t and do the comparison, which is an implementation defined mapping, but it like isn't going to map two pointers that are different to the same value. It's not allowed to do that. Either way, I'm not really sure.
Currently, the use of in a union to use a member of the union, which is not the active union member, is undefined behavior. Do you have an opinion on that?
So currently, so the question was, I was explaining the question without first saying that. Yeah. So the question was accessing the non-active member of a union is currently undefined behavior. And what are my thoughts on that, or opinion on that? Well, there are things that that implementation can do that I'm trying to think of a good example here. So it's not just that that compilers can take advantage of this. Like LLVM explicitly doesn't take advantage of this, and I think GCC doesn't either.
GCC documents in the documents they don't take advantage of.
Yeah. And so LLVM does the same thing, probably because of GCC. Now the problem with like making it well-defined behavior is an example here might be like a float and an int. Like you might try to access it as a float, but it was actually a trap value. And now you've got a trap value and well, whatever can happen. And that sense, you don't know what the active member is. You might not actually be able to like guarantee a certain behavior there. We could say unspecified behavior, but I don't know how hard it would be to make that well-defined.
And some optimizers do change the value sometimes, right? So GC had a bug a while ago where the first member was a floating point thing and second was an integer of a union. If you just use the int, it would pass it around, and if it happened the union was a singling, then it would flip the int to another value. So like LVM ran into that, but combining LVM with GCC would cause it to do the wrong thing.
So if I'm able to summarize that, there's a problem with actually was a union of an int and a float, and if you even only accessing the integer part, it would, I actually missed, like it would write a different value or?
We would use the FPU to load and store.
Oh, while using it as an integer, it would use the FPU to do loads and stores. And if that int became a bad value, then you got this weird behavior.
Also, in order to make the union switch valid, the standard would have to force choose complement. Otherwise, the unsigned to int would be, would not be predictable, or at least would be implementation defined, as well as alignment.
Yeah. So if we were to give like full well specified to that, we would also have to like specify unsigned to signed conversion and alignment, all these things. But in more generally, yeah, you'd have to say like when you take this bit value and put in this bit value or in this other type, like what does that mean for basically every conversion? Any other questions? Okay, I think we're good.